The directions say to find a function small f such that capital F is equal to the gradient of small f. Evaluate the integral over c of f dot dr along the given curve c. In example 1, suppose f of xy is equal to 3 plus 2xy squared I plus 2x squared yj. So we have this given vector field. C is the arc of the hyperbola y equals 1 over x from 1, 1 to 4, 1/4. So what we're going to do is we're going to let p equal 3 plus 2xy squared, and we're going to let q equal 2x squared y. So we're setting p equal to the first component of the vector field, and we're letting q equal the second component of the vector field. The partial of p with respect to y is equal to 4xy. The partial of q with respect to x is equal to 4xy. Since the partial of p with respect to y is equal to the partial of q with respect to x, f is a conservative vector field. So in the second part of this, we want to find the potential function small f. So what we're going to do is set the partial of f with respect to x equal to 3 plus 2xy squared. And let's note y is fixed. So f of xy is equal to 3x plus x squared y squared plus g of y. So g of y is like my constant, okay? Now, what I'm going to do is take the partial of f with respect to y. That's equal to 2x squared y plus g prime of y. And so we're going to set 2x squared y plus g prime of y equal to 2x squared y. And if we go back, remember 2x squared y is the second component of this vector field. And we're setting it equal to 2x squared y so we can get a handle on g of y. So again, set 2x squared y plus g prime of y equal to 2x squared y. So that says g prime of y equals 0, and so g of y equals k. Now, we're going to take k equal to 0, and I'm going to explain that in a minute. So f of xy is equal to 3x plus x squared y squared. And remember, I took k to be 0. Now keep in mind, I'm trying to figure out the integral over c of f dot dr along a certain path from the point 1, 1 to the point 4, 1/4. If I just wanted the potential function f, I would have added k to the end and have been done. But there's a second part of this question where we have to apply the fundamental theorem of line integrals. And I want to give you this analogy. If we were doing an indefinite integral, okay, so for example, I wanted the integral of cosine x dx. I would have said sine of x plus c, so I would have added a constant, right? If I wanted to compute a definite integral, so I have a lower limit and an upper limit. And so let's say I wanted the integral from 1 to 2 of x dx. Now, if you guys remember, when I have the integral from 1 to 2 of x dx, I get 1/2 x squared evaluated from 1 to 2, right? And I would have replaced x with 2, replaced x with 1, and subtracted the results. Now, for the record, I could have easily have said 1/2 x squared plus 5 from 1 to 2, and replace x with 2 and x with 1 and subtracted the results. But what happened to that 5? That 5 ends up canceling. So it will end up canceling anyway. And when we apply the fundamental theorem of line integrals down below, if I have a k here, that's fine. When I go to take f of 4/1/4 and f of 1/1 and subtract those values, the k will end up canceling anyway. And that's why we end up taking k to be 0. It's the same idea when we do a definite integral. It's not necessary to add that constant c. We just need an antiderivative that works when you do the definite integral. And when you apply the fundamental theorem of line integrals, you just need a potential function that works. I hope that makes sense. So in short, we're going to take k equal to 0 as a point of convenience. And so f of xy is equal to 3x plus x squared y squared. And so the integral over c of f dot dr is the integral over c of the gradient of f dot dr. And that's equal to f of 4/1/4 minus f of 1/1. So we just needed to evaluate the endpoints. And that's the power of knowing that you have a conservative vector field. We just needed to consider the endpoints, and the curve became inconsequential. Now, f of 4/1/4 is equal to 13. F of 1/1 is equal to 4. And so the integral over c of f dot dr is 13 minus 4, which is equal to 9. And in short, that's example 1. So again, I took k to be 0 because I just needed a potential function that works. And it's because we have a second part to this problem where we're essentially applying the fundamental theorem of line integrals. Okay, let's take a look at example 2. It's a slightly harder example, and it's a function of 3 variables this time. So f of xyz is equal to the vector field where the first component is y squared z plus 2xz squared. The second component is 2xyz, and the third component is xy squared plus 2x squared z. The curve is defined by the parametric equations x equals square root of t, y equals t plus 1, and z equals t squared, where t is greater than or equal to 0 and less than or equal to 1. In section 16.5, we will learn how to show f is a conservative vector field. And so, just for full disclosure, I'm taking these problems out of the Stewart Calculus textbook, and in 16.5, that's where we cover how to show that you have a conservative vector field. So for sake of argument for this problem, I'm going to assume that f is a conservative vector field. And we're going to now focus on how to find that potential function. So to find small f, we're going to set the partial of f with respect to x equal to y squared z plus 2xz squared. So in this case, y and z are fixed. Think of them as constants. From here, we're going to look at f of xyz. F of xyz is xy squared z plus x squared z squared plus g of yz. From here, we're going to take the partial of f with respect to y. The partial of f with respect to y is 2xyz plus g sub y of yz. So remember, g of yz is a function of 2 variables. And so when we take the partial of f with respect to y, you're looking at essentially a partial derivative, and that's why I'm writing it as g sub y of yz. So from here, we're going to set 2xyz plus g sub y of yz equal to the second component of that vector field, which is 2xyz. So the 2xyz's cancel, and then from here, we have g sub y of yz equals 0, and keep in mind that z is fixed. So g of yz is equal to h of z. Therefore, f of xyz is equal to xy squared z plus x squared z squared plus h of z. And then from here, we're going to use the third component of the vector field to get a handle on this h of z. So take the partial of f with respect to z. We get xy squared plus 2x squared z plus h prime of z. Set xy squared plus 2x squared z plus h prime of z equal to the third component of that vector field, which is xy squared plus 2x squared z. And so notice how the xy squareds cancel, the 2x squared z's cancel, and we get h prime of z equals 0. That says h of z is equal to k, and just like in that first example, I'm going to take k to equal 0. I just need a potential function that works because we're going to be doing a second part to this question. So f of xyz is equal to xy squared z plus x squared z squared. So let's remind ourselves of what this curve is. So C is defined by the parametric equations x equals square root of t, y equals t plus 1, and z equals t squared. And remember, t is greater than or equal to 0 and less than or equal to 1. Okay? Now, from here, r of t, so we're going to define this vector valued function. R of t is a vector where the first component is square root of t, the second component is t plus 1, and the third component is t squared. R of 0, right? This is equal to the vector 0, 1, 0. R of 1 is equal to the vector 1, 2, 1. So the integral over c of f dot dr is equal to the integral over c of the gradient of f dot dr. But by the fundamental theorem, this is equal to f of r of 1 minus f of r of 0. And then I just plugged this in accordingly, and I ended up getting 5. And that's example 2. Now, before we end this video, I want to go back on finding these potential functions. Okay, so remember back here, we assume f is a conservative vector field. We have to assume that for sake of argument. Now, to find my potential function, keep in mind, I'm setting the partial of f with respect to x equal to the first component of that vector field. And that first component is y squared z plus 2xz squared. And from here, I'm trying to find f of xyz. But remember, y and z are fixed. Okay? And so when we find f of xyz, what I'm really doing is taking a partial integral. So in other words, I'm looking at the partial integral of y squared z plus 2xz squared dx. Okay? Now, if y and z are fixed, sine of y is fixed, y squared is fixed, z is fixed, cosine of y plus sine of z is fixed. You have to capture all those fixed values. And the way to capture that is this g of yz. That's my constant. So when I found f of x, y, z, you're not adding a constant like that we're used to in Calc 1. We're adding like a function of y and z, because y and z are my fixed variables. And then, so notice how I set the partial of f with respect to x equal to the first component. I integrated essentially to get f. Then I take the partial derivative of f with respect to y. And so notice I integrate, differentiate, set equal. Integrate, right? From here to here, I integrate. From here to here, I differentiate. And then I set equal, right? I set two things equal to each other, in other words. That's the pattern to these. Okay, that's going to do it for this video. And this is a video on the fundamental theorem of line integrals. Okay, thank you.